inverse means the opposite. Additive inverses are when you add two terms together and they sum to 0. So -4, positive x, -5x, and -8y. And 5, 6, and 7, our goal was to substitute. So you basically said that x is equal to 2y minus 1. So everywhere you have an x, you wanted to replace it with 2y minus 1. And then after you replace it, you wanted to solve for y. So you were going to combine like terms. So I would add my y's together, move my numbers to the same side, divide any coefficients out, and we got y equals 1 in the first problem. Similarly, in number 6, you needed to distribute that negative 2 to both terms. So the -2 is out in front. The x becomes that 2y minus 1. So you got y minus 4y plus 2 equals 8. So you got -3y equals 6. And you get y equals -2. So again, that -2 does not go away. It gets multiplied and distributed in. Same with the +3. So combine like terms, distribute, and simplify. Are we okay with substituting? So what we're going to do today is learn a system of solving equations algebraically. So right before break, what we did was graphically solve our systems. So when you graphically solved a system, you graphed both equations on one graph and you look for, do they intersect or do they not intersect? If they intersected, then they had one solution. If they did not intersect, then you look to see if they were parallel or the same line. So they either had no solutions or infinite solutions. So what we're going to do today is compare two more complicated equations that we can't really graph, so don't graph paper, or that solving them for y equals every time would not be as nice. So this is what we call the substitution method for solving linear or any algebraic equations. In this chapter, we're going to focus on linear. So what you do is solve one equation for one of the variables. You want to, if you can, solve for the variable that does not have a coefficient on it. Then you are going to substitute the expression into the other expression, solve for that equation, and then substitute it back. So you should get two answers, an x and a y. So let's go through a couple of examples. So looking at those two equations in example number 1, what I notice is that in the second equation, the y value has a coefficient of 1. So what I want to do is solve the bottom equation for y. So I'm going to solve the bottom equation for y. And that gives y equals -2x plus 7. Then, just like in the warm-up, I'm going to take the -2x and substitute it in for y in the other equation. So I solve for a variable, then replace that variable in the second equation. So you get 5x minus 3 times negative 2x plus 7 equals 23. Now I'm going to solve for x. And I get x equals 4. Now, in the warm-up, it only asks you to solve for y. Now, this says to solve each system. So to solve the system, I need to solve both for x and for y. So I'm going to take that x value, and I'm going to plug it in to x in the other equation and solve for y. Technically, you can also plug it in here where you have your y solved for. Both should work. The only problem is if you made a mistake solving for that y, then you're going to continue making that mistake. So I have a tendency to always plug back into the original. So you get 2 times 4 plus y equals 7. So you get 8 plus y equals 7. So you get y equals 7 minus 8. Or y equals negative 1. Now, what I should be able to do, and to check quickly, is to take that negative 1 and that positive 4, and if I plug them in to the other equation, it should be true. So 5 times 4 is 20, negative 3 times negative 1 is positive 3, 20 plus 3 is in fact 23. So you should be able to take the answer you get, check it in the other equation, and ensure that it is true. So if I were to have graphed these two lines, these would have been intersecting lines. They have one solution. That one solution is 4, negative 1. That represents that ordered pair that if you had graphed them, you would have seen. Make sense? So what we're doing today directly goes back to what we did prior to break, but now we're just using equations instead of graphs. So in the next one, both x and y in that bottom equation have coefficients of 1, so it doesn't matter which one you choose to solve for. Since we previously solved for y, I'll solve for x. So you would subtract y to the other side. So I get x equals negative y minus 12. I'm going to take that answer and plug it in for x in the top equation. Since I solved for x, I'm going to replace x. So you get 2 times negative 12 minus y minus 3y equals 6. Negative 24 minus 2y minus 3y equals 6. Negative 24 minus 5y equals 6. Add 24 to both sides. Negative 5y equals 30 over negative 5. So you get y equals negative 6. Once again, my final answer has to have an x and a y. So I'm going to take that y, plug it back in, and I get x minus 6 equals negative 12. Add 6 to both sides, and I get x also is negative 6. So that is the ordered pair, negative 6, negative 6. once again, intersecting, independent, one solution. Solve. So you can add. You don't have to solve necessarily with the value on the left. You can solve with it on the right as well. So in this case, it's easier to add y to the other side. But once again, I'm going to replace y with 3x. So you get 2 and 6. Okay. Oftentimes you are going to see systems of equations not necessarily as 2 sets of easy equations, but more as word problems. Most systems of equations are representative of things that happen with word problems. So, for example, we have a pizza shop. They have 2 specials. The first special is a soda and 2 slices of pizza. So what you want to do is identify your variables. So I'm going to have x represent soda and y represent number of slices of pizza. So I have to define my variables. I need to know what each variable represents. Once I know what they represent, I'll create my equations. So the first equation is a soda, so that's like 1x, plus 2 slices, so 2y, cost 10.25, so equals 10.25. The second equation is a soda and 4 slices is 18.75. So I have 2 deals. What I want to do is figure out what the cost is per item. So I'm going to solve one of them for x. It doesn't matter which one. And then use that to solve for y. So maybe I solve the first one. So you get 10.25 minus 2y equals x. So then here, 10.25 minus 2y plus 4y equals 18.75. Combine like terms, subtract the other value away. So you get 2y equals 850. So divide by 2, and I get y equals 425. So what that means is a slice of pizza costs $4.25. So that is a numerical or a money value. So we would want to make sure we include our units because that is the cost of the item. And then to solve for x, you would go back and plug in 4.25 for y. So you get x equals 10.25 minus 2y, which is 850. And we see that a soda costs $1.75. I was thinking about when I printed these that I should really update my things. I don't feel like anybody buys CDs anymore. So it says you can buy CDs at a local store for $15.49. You can buy them online for $13.99, but pay $6 shipping. Find the number of CDs that you can buy at the store and online that would cost the same. So you want to know how many CDs you can buy that would cost the same. So we'll say that X equals the number of CDs. But in this case, well, we could still use Y, but I would use a C and have that represent the total cost. So the cost of purchasing in store would be 15.49x. The cost of purchasing online would be $13.99x plus that single fee of shipping, which is $6. So when something only occurs one time, that is like your initial value or your starting position. It is not going to be affected by the variable. What's nice about this problem is you already have both equations solved for one of your variables. So you're just going to take one and replace it for the other. So since I want to know when they cost the same at each store, I need 15.49x to equal 13.99x plus 6. So you're going to get all the x's on the left. So you get 4. So if he buys 4 CDs online or in store, the cost is the same. And then if you want to know what the cost is, you would take C equals, plug 4 into either equation, it does not matter. So like 6196 maybe? Right down the front. So again, all of these problems are for application in real world situations, things that you can actually determine or possibly use. So their homework is listed on the outline. The problems are a little bit scattered because the textbook has substitution and elimination in the same section. So today we did substitution, tomorrow we're going to do elimination,